So here we go. Talking about position and displacement still. So if we're going to define position like in words, we might say something along the line of that it's relative to the origin. Am I off screen? Oh, let's put it on screen. That's a bit of a tease. Relative to the origin. It's related to the directional reference frame. And we've talked about the fact that there are a variety of appropriate directional reference frames depending on context. It's going to have magnitude in units. And an example might be the ball landed 12.0 meters away to the east of the tree. I know that's kind of mundane, but that's an example. Oh, what's...
Please excuse this interruption. Could we please have all grade 10 classes make their way down to the large gym for the assembly? Once again, all grade 10 classes, please make your way down to the large gym for the assembly. Thank you.
All right. And then displacement, if we were going to put it into words, it's how far and in what direction is one point from another point. So we've got direction associated with it, we've got units, and we have magnitude. And you know, I saw this one time, full disclosure, I stole this from a textbook, but somebody had drawn what was supposed to be an ant colony. And this ant colony ended up being like this splintering web. And depending on the resolution of the print job that you have, you can see like all these A, B, C, Ds or whatever that label all the branching pathways or tunnels of this ant colony. And it could be that the opening to the anthill is the origin. That could be the beginning part. But we might talk about, here I've got position B and position A. I'll relabel them because my resolution's a little on the fuzzy side there. And somebody might say, well, what's the distance from position A to position B? Well, distance is measured by following the path. See how my pen is following the path? I take a path, and if I were to measure that, that would be the distance, that I've traced out with my pen. You see what I mean? The displacement, on the other hand, is if I go from A to B, that would be my displacement vector. And the ant has to follow the tunnels. That's fine, but if we want to know what the displacement is from one point in this anthill to another, we're talking about like just straight through the dirt. What's the displacement? How much of it has it been displaced? Now, I don't know how much that really matters for ants, but if this was an underground bunker or something like that where humans live, we might actually care. It might be that there's a Wi-Fi hub at position A and there's an internet connection at position B. Maybe the Wi-Fi can only penetrate through Earth at a certain distance, and we might care about the displacement. That might actually be an issue, you know what I mean? That's not how ants communicate. They communicate through pheromones, which are airborne. So, I mean, like that's like a little bit about ants, I guess. But I don't know why you would care about displacement for ants. I just saw it in the textbook and I thought it was cute, right? Distance versus displacement. So if we're differentiating, this is displacement. I'll do it in red. This would be the path for distance for that same ant. Now, if I wanted to calculate the distance, I'd have to sit in there with like a little ant-sized tape measurer and measure it out, you know? Or maybe like run a string from point A to point B and then measure how long that string was. Or, you know, there's some creative things we could do here, right? For displacement, though, I might actually find this angle, find the x component, find the y component, and do some Pythagorean theorem. That could be a thing that I would do. And I don't want to camp on this for very long. I just want to sort of like, again, see like another visual of what the difference is between these different terms that sound similar but aren't quite the same. And guys, I saw a hand at the back. What's up?
Last sentence, direction units, what is that symbol next to?
Oh, it's the and symbol. And magnitude. Yeah. All right, so a little bit more human and a little bit less antish. I got a person. This person's going to walk in the hallway. And let's say that it's the hallway right outside this classroom. And so in terms of the reference frame, we might say up. Notice that it's not north, it's up, because this is a side view. So situationally, up. I'm going to make it be positive, and we could make down be negative. Now, just to be difficult, I'm going to say that to the right isn't right anymore. I'm going to say, hey, this hallway is perfectly lined up with the east-west axis. So this person walking up and down the hallway is going to be walking east. They're walking east right now. And maybe they're walking from geography class. You know, geography's at the other end of the hallway, and they're walking from geography class to physics, right? Had some geography earlier, going to go off to the next period, going to go to physics. And so west is where they're walking away from, leaving geography, going towards physics, and we'll make east be positive and west be negative. Now, if this person's traveling towards the east, I'm going to start off with a vector diagram here. I've got my clear ruler. I'm going to say, okay, well, this person's going to be going this way. I'm going to say this person travels east. Displacement 1 is equal to 50.0 meters. Now we all know, because we ran up and down this hallway, that the hallway is more than 80 meters. It's actually about 120 meters long. Okay, so our hallway happens to be 120 meters long. That's a piece of trivia for our school. Now you know. Okay, 120 meter long hallway. Okay, but say they left geography, 50 meters of traveling east, and then they're like, oh wait, I forgot my physics textbook. And they turn around and they start walking back towards their physics room, or their geography room. And then they're part way back. About 30 meters. And somebody says to them, hey, bro, I got you. And your good friend picked up your physics textbook. You're like, oh, thank you very much, good friend. Let's skip back to physics. Everybody skips to physics. You always skip to places that give you joy. Right? And we head back to physics. Well, as we head back to physics, we were almost there before anyway. And displacement 3 ends up being 40.0 meters. Now, as I look at this, I think to myself, wait a minute. Yeah, the 50 meters was east, so that's positive. The 30 meters was west, maybe that should be negative. The 40 meters was positive. I'm adding these positive and negative signs in red just to remind ourselves. The diagram actually tells us which direction is positive and negative, so we don't really have to add them on right now. But if I'm using this as a list of givens, then it makes sense that I would add the positives and negatives. And somebody comes along and says, hey, could you please calculate the displacement that this student walked? And they say, oh yeah, wait, no problem, I can do that. Delta D total, that's what the subscript T is for total. Displacement total. The total displacement is the sum of all your little displacements. Displacement 1, displacement 2, displacement 3. And then we kind of wrote a list of givens, so we can say, all right, well, displacement 1, positive 50 meters. And if you want to write the positive, you can. And if you want to write it as minus 30 meters, you can, or you could say minus or plus negative 30 meters. Either way, floats my boat. Plus 40.0 meters. And notice that all of the directions have been translated to math already. I didn't even bother writing 30 meters west and 50 meters east. I'm translating to physics speak, to math language right away, just because it makes it all easier for me. And somebody who's quick with the head math, what's the displacement of this walker? Yes, sir.
60.
60 meters, yeah.
60 meters east.
Beautiful. You read my mind. Right? So 60 meters is positive, so it says 60 meters east. I'm not even going to say approximately, because it's exact this time. There's no rounding that's gone on here. I am obeying significant digits rules, but it was easy this time. All right, and then somebody else comes along and says, wait a minute, you calculated the displacement, but I'm really into fitness. I want to know how many steps that I take each day. You know, I'm one of these Fitbit tracker type people. My Google Fit app is always on. Could you please calculate the distance? Yeah, no problem. The variable for distance, unfortunately, looks almost identical to the variable for displacement. What's the subtle difference? No arrow, yeah. Notice that the arrow, the directionality is missing, right? So when I go to write the formula, again, you know, whether it's good for you or bad for you, I'm sorry if it's bad for you, the formula looks almost exactly the same, but all of these D's are missing arrows now. Now, since they're missing arrows, I don't have to indicate direction, either in my language or with my math. So I'm, you know, as the math people would say, I'm only concerned about the magnitude, right? So I'd say, okay, well, 50 meters is just 50 meters. Never mind the plus or minus. Negative 30 meters is just 30 meters, because it's just how many steps I took. Same with the 40. And then somebody else who's quick with the head math. What's my distance? 120, yeah. 120. I'm not worried about positives or negatives. 120.0 meters. And you notice that I don't have to write the direction. That's a distance. It's not a displacement. There's no directional information. The first piece of information tells me how far and in what direction am I relative to geography class when I get to physics. The other one tells me how much walking did I do? Distance, displacement. Now in everyday speech, a lot of people think distance and displacements are the same thing. The variables even look similar. But clearly, like, one is twice as big as the other in this case, right? Here's the question. Could the distance and the displacement ever be the same value?
Yeah.
Yeah? What would somebody tell me, what would have to be true? Say it out loud.
One displacement.
Sorry?
Like walk in a straight line and not go back and stuff.
Yeah. Walk in a straight line, never double back on yourself. That's the only way distance and displacement could be the same. Is there any way that the displacement could be bigger than the distance? Not in my universe. The only way I can think of where displacement and distance could be different and displacement could be bigger is this universe, where I walk here and I end up here, and there was actually a vortex here, and I only walked like 2 meters, and then I ended up over here, which was actually like 30 meters away. So in the absence of teleportation and wormholes, you're never going to end up having a displacement that's greater than a distance. Everybody cool with that? All right, so as long as we stay away from wormholes, can we all say, I'm going to ask you to make a pledge, and you're going to say, I do, okay? Can everybody please pledge to not walk through the vortex if you see it?
I do.
I do. Okay, good. So don't walk towards that light unless it feels good, I guess. All right. I need whiteout because I got to get rid of this vortex, which looks suspiciously like a paperclip, actually. But anyway, so maybe that's a good tip. Stay away from paperclips because they might be small vortices. All right, so velocity. Let's just say this whole thing, new information. The whole thing took 95.2 seconds, okay? So you're walking up and down this hallway, new information. Somebody says, hey, could you tell me the velocity of this person? They say, yeah, no problem. The average velocity. By the way, I'm going to write the whole word average in the subscript here. But moving forward, you're going to be allowed to just write AVG. AVG, short form for average. Okay, I'll do it in a minute, but like this one time, can you write the whole word average? The average velocity is defined as the total displacement divided by how much time goes by for that displacement to occur. Okay? And so if I was going to calculate the average velocity for this walker, it would end up being here I'm going to short form it, V average equals positive, remember there's a positive sign when I'm mathifying this, positive 60.0 meters divided by 95.2 seconds. And somebody with a calculator who's quick on the draw, what do you get? Whoa, I'm overwhelmed. What's the answer?
0.63.
Okay. 0.63. Is it 6.30? 0.630? 30, okay. And then the units are going to be meters per second. You know, I'm tempted to write positive there, but I think I'm just going to jump straight to human language. What does the positive represent? East. So I'm going to write east. That was that person's average velocity. Okay. Now, if I want to calculate speed, you notice average velocity uses displacement. So it's a vector value that's based on another vector value. Average speed has the same formula. Oh shoot, I almost put an arrow over top of it. V average with no arrow is equal to delta D with no arrow, total, divided by delta T. And that's going to be equal to 120.0 meters divided by 95.2 seconds. And again, somebody with a calculator, what's this person's average speed? 2 point? Is it?
1.260.
Oh yeah, 1.260. 1.260 meters per second. Now I got to obey my significant figures rules. Notice there's only 3 sig figs on the time. So this is an easy round off. 1.26 meters per second. But you notice that because it's a scalar, there's no direction. And I could say that this guy here, speed, is based on distance. So a scalar based on another scalar. And that differentiates the displacement, or sorry, the speed and the velocity. I gotta ask the room. Can I switch the page? People need a second? Yeah. All right. People that are ready, turn over to the next page. Let's take a look. We got a question at the top of the page that has to do with doing some chores and walking back and forth. This is a side view, kind of like the first sailboat we looked at, but it's a side view of a person walking between a mall, a home, school, and a library. I'm going to switch the page here. And it looks like we're telling a story. And a lot of physics problems are kind of telling a narrative, right? And I think that sometimes that creates a distinction between just doing math and doing the sciences, is that science always happens in a context, right? So the context here is we're doing some chores. We're starting out at position 1, that's home. Then we're going to position 2, that's school. Library, that's 3. And then the final position is the mall. So here I am, I'm using that word position. And as I travel along, I'm experiencing a distance and displacement change for me as a chore doer. So we've got a scenario that connects these things, and we're going to travel from position 1, 2, 3 to 4. Now, what I'm going to suggest is if we have a reference frame, could we just define one direction as positive and one direction as negative right from the beginning? Okay? So I've got an east and a west. Now, it doesn't matter this time, but this isn't north and south, this is up and down, right? Because this person stays on the ground the whole time, so it doesn't matter that there's an up and down, we can just use the east and west. But just to make it clear, up and down and north and south are not the same thing, right? So we just got to make sure that's out of the way. It looks like it's going to take 2 hours. So maybe that's something we should deal with. We've got to deal with the fact that time isn't like perfectly metric. I would like to turn it into seconds. So if I have 2 hours, one thing that I know is that 1 hour, how many minutes are there in an hour? 60. Now I'm going to do something here, and it'll make sense in a minute, okay? I'm going to say 1 hour times 60 minutes per hour. How many seconds are there in a minute? 60, yep. Times 60 seconds per minute. And the reason I'm doing this is I want to have a really systematic way to figure out how many seconds there are in an hour. And I want to point this out. If I multiply these facts together, what's going to happen is, notice that the minutes are going to cancel out. One's in the numerator, one's in the denominator. This is a chain of cancellation. The denominator and the numerator cancel, cancel. Notice that the hours are one in the numerator, one in the denominator. Cancel, cancel. And what that means is that I can calculate how many seconds there are in a minute very easily. Somebody help me out. How many seconds are there in a minute?
7,000.
No. No, calculate it. It's 3,600. 60 times 60 times 1 if you like is 3,600 And the only unit that's left over here is seconds. So there's 3,600 seconds in an hour. Okay? Now the reason that's important is because down here, we're traveling for 2 hours. Okay? So this whole thing takes us 2 hours. And the person that said 7,200, I know what you're thinking. You've already done the math for us. We're saying that there's 2 hours here. And so 2 times the 3,600 is going to give us 7,200 seconds. All right? Now the question here is, though, to find the distance and displacement. So let's just say we want to find what our total distance is for this trip. I want to ask you guys to do this. This is just like walking up and down the hallway in our problem earlier. Could you please, if we go in the order 1, 2, 3, 4, could you please list out delta D? I'm going to call it from home to school. I'm going to call that displacement 1. Delta D2 is going to be from school to the library. So let's call this 1, 2, and then back, 3, okay? So could you please jot down, and you're going to have to do a little bit of thinking for displacement 3. Not a lot. Let's give these guys arrows. Somebody help me out. What's displacement 1 equal to? Yes, sir.
500 meters?
500, and even we could say positive 500, right?
Yeah.
So we'll attach that math speak to it right away. Positive 500.0 meters. Somebody else. Displacement 2. Shout it out. 700. Positive 700 meters. Looks like it, right? 1,200 minus 500. See that? And then displacement 3.
1,700.
Is it?
800.
It's hard to say.
I thought the mall ends down at school.
You think so? Like from here to here?
Yeah.
I was thinking it was here. Can we just say that that's 1,000 meters there?
Yeah.
Let's declare that to be 1,000 meters, because it looks like our diagram's a little ambiguous. It's hard to tell, you know? But if that's the case, wouldn't it be 2,200 meters west? Okay. So negative 2,200 meters. All right, now this whole thing takes 7,200 seconds. We've got our displacements. From our displacements, we could just like strip away the negative and positive signs and make them into distances. Can you guys please take a second? Could you find the displacement? Work with a buddy. Find the displacement, find the distance. Now, before we do that, though, as a part B, because I'm going to put the answers up, don't worry, but as a part B, I'd like you to also figure out, we got a scale here that 1 block is equal to 250 meters. So this is another partner's challenge. I want you to figure out, please, could you figure out what the displacement is for if we were to do chores in this neighborhood? So this neighborhood is a one-dimensional neighborhood. This neighborhood is a two-dimensional neighborhood. Okay? It's like we're rising up. And it turns out that the universe that we live in, believe it or not, it might even be higher than this, but at a minimum, the universe I live in is three-dimensional, right? So it makes sense that I should be able to do the one-dimensional universe. I don't even know what that world would be like to live in. I'd like you to also try to find the displacements between 1 and 2, from 2 to 3, and from 3 to 4. Don't find anything else out just yet. Just find the displacements in the two-dimensional universe. We'll try to scale things up to a clearer vision of reality, okay? I'm going to stop my recording, and then we'll carry on, okay? And I'll turn the lights up.